72 hours. That's the window astronomers say we have before whatever the James Webb Space Telescope captured last month becomes the most discussed observation in modern astronomy, or quietly disappears into the archive of anomalies that never quite added up. The data exists. The spectral readout exists. The internal correspondence between Goddard and the Space Telescope Science Institute exists. What hasn't existed until now is a public explanation. And the closer we get to the scheduled embargo review, the louder a particular question becomes. What exactly did Webb see when it pointed its near-infrared spectrograph at the closest star to our Sun? And why is the release timeline being treated with a caution that almost no other JWST observation has received? To understand why a single spectroscopic anomaly from Proxima Centauri has rippled through the astrobiology community, you have to go back to the architecture of the instrument itself, and to the history of what happens when humanity points its best ear, or its best eye, at that particular star. Webb launched on Christmas Day of 2021, after years of delays that nearly killed the program. It rode an Ariane 5 out of French Guiana and unfolded itself across 1 million miles of empty space until it parked at the second Lagrange point, the gravitational saddle behind Earth, where the Sun, the planet, and the telescope all orbit in a stable choreography. Its primary mirror, 6.5 meters across, gold-coated and segmented into 18 hexagonal panels, was built to do one thing that Hubble could never do well. It was built to see infrared, heat, the faint, low-energy light from objects too cold, too distant, or too obscured to register in visible wavelengths. Galaxies from the first 100 million years after the Big Bang, dust clouds wrapped around forming planets, and importantly, the atmospheres of worlds orbiting other stars. The instrument that captured the anomaly is called NIR-SPEC, the Near-Infrared Spectrograph. It splits incoming light into its component wavelengths, the way a prism splits sunlight, but with a precision fine enough to read the chemical fingerprint of a planet's atmosphere from light years away. When a planet passes in front of its parent star, some of the starlight filters through the planet's air on its way to Webb. Each molecule in that air absorbs a specific set of wavelengths, leaving dark gaps in the spectrum. Oxygen leaves one signature, methane another, water vapor another still. An IR-SPEC was designed to read those signatures. And in late March of this year, during a scheduled observation window of the Proxima Centauri system, it appears to have read something that didn't fit any known template. Now here is where the story gets careful, and where it needs to stay careful. Because Proxima Centauri has a history. A complicated, embarrassing, fascinating history with signals that turn out to be something other than what we hoped. Proxima Centauri is a red dwarf, an M5.5v in the technical classification, which means it's small, cool, dim, and astronomically common. Most stars in the Milky Way are red dwarfs. It sits 4.246 light-years from Earth, which makes it our nearest stellar neighbor outside the Sun. And we know, with confidence, that it has planets. Proxima b was confirmed in 2016 by a team using the European Southern Observatory's HARPS instrument, an Earth mass world circling within the habitable zone, the region where liquid water could, in principle, exist on a rocky surface. Proxima c followed, a heavier world farther out. Proxima d, smaller and closer, and was added more recently. 3 confirmed planets around the closest star to home. You cannot design a more tantalizing target for the search for life beyond Earth, which brings us to BLC-1, Breakthrough Listen Candidate 1. In April of 2019, the Parkes Radio Telescope in Australia, working as part of the Breakthrough Listen initiative, recorded a narrowband radio signal at 982 MHz coming from the direction of Proxima Centauri. Narrowband signals are interesting because nature doesn't usually produce them. Stars produce broadband noise. Quasars produce broadband noise. A signal compressed into a sliver of the radio spectrum tends to be artificial, which is why narrowband transmissions are exactly what SETI researchers have spent decades looking for. The signal drifted in frequency the way a real astronomical source would as the Earth rotated. It seemed for a while to be the most promising candidate technosignature ever recorded. Then Dr. Sophia Sheikh, working at Penn State, led a careful reanalysis. Her team's paper, published in Nature Astronomy in October of 2021, concluded that BLC1 was almost certainly local radio frequency interference. Some piece of human electronics, somewhere on or near the Australian site, leaking signal into the dish in a way that mimicked an extraterrestrial source. It was a quiet, professional retraction. No drama. Just careful work showing that the signal had similar features at frequencies that ruled out a true Proxima origin. Dr. Andrew Simeon, who directs Breakthrough Listen out of the Berkeley SETI Research Center, called the result exactly what science should look like: excitement, scrutiny, reassessment. The WOW signal of 1977, the famous narrowband burst recorded by Ohio State's Big Ear telescope, remains unexplained to this day, but most signals that look extraordinary turn out to have ordinary explanations. BLC1 was one of them. So when reports began circulating in the small Slack channels and conference back channels where this kind of thing always circulates first, that NIR spec had recorded an unusual feature in the Proxima Centauri spectrum, the response inside the astrobiology community was not excitement. It was caution. Burned one's caution. The kind of caution that comes from a discipline that has been here before and remembers exactly how it ended. What makes this case different, according to multiple researchers familiar with the observation, is the nature of the anomaly itself. It is not a radio signal. JWST does not observe in radio. It observes in infrared, which is a fundamentally different kind of measurement. What NIR spec apparently recorded was a spectral feature, an absorption, or emission line at a wavelength that does not match any standard atmospheric or stellar template. According to the protocol governing JWST data releases, observations of high astrobiological significance go through an internal review before public dissemination. That review is intended to catch instrument artifacts before they become headlines. It is the lesson the field learned from BLC1 and from a dozen earlier false alarms, including the original interpretation of phosphine in the atmosphere of Venus, a claim that has been contested, retracted, in part, and revised across half a dozen papers since 2020. The current status of the Proxima Centauri NIR spec observation, based on what can be pieced together from public statements and the absence of public statements, is that the data is embargoed pending peer review. That is not the same as being hidden. Embargoes in astronomy are routine. Most major observations have a proprietary period during which the team that proposed the observation has exclusive access, typically 12 months before the data becomes public. What is unusual here is not the existence of an embargo. It is the chatter around it. Let me describe what we appear to know, while keeping in mind that almost all of it is unconfirmed in the formal sense. During a scheduled transit observation of Proxima b, the NIR spec instrument recorded a series of spectral features that the initial automated pipeline flagged as inconsistent with the expected stellar background. The features appeared in the wavelength range associated with certain molecular vibrational modes, but the specific pattern did not match the standard library of expected absorption lines for water, methane, carbon dioxide, or any of the other usual atmospheric constituents. The team running the observation, working under the standard JWST proprietary period, declined to make any public statement beyond confirming that data had been collected and was being analyzed. The Space Telescope Science Institute, which manages JWST operations, has not commented on the specifics. NASA's astrobiology program has not commented. This is where the temptation to fill the silence with speculation becomes overwhelming. and where the discipline of staying inside what evidence actually supports becomes most important. The skeptic in this story, and every responsible version of this story needs one, is Dr. Jason Wright. He's an astronomer at Penn State, the same institution where Dr. Sheik did her BLC-1 work, and he has spent a career thinking carefully about what counts as evidence for extraterrestrial technology and what doesn't. His position on the current Proxima Centauri reports, summarized from his public writing and his general approach to extraordinary claims, is that the most likely explanations are instrumental. Calibration drift, in which the detector's response shifts slightly over time and produces apparent features that aren't really there. Zodiacal scattering, in which dust in our own solar system scatters infrared light in ways that can imitate distant signals. Cosmic ray hits on the detector array, which can produce isolated spikes that look spectroscopic but are noise. Order overlap, in which light from one part of the spectrum bleeds into another and creates false features. He points out correctly that JWST is a young instrument, that its quirks are still being mapped, and that the first year of operations produced multiple anomalies that turned out to be calibration issues rather than genuine astrophysics. Dr. Wright's caution is shared by most of the people qualified to comment. The standard quote, repeated almost verbatim by several researchers asked about the situation, is some version of extraordinary claims require extraordinary evidence. That phrase, originally Carl Sagan's, has become the load-bearing wall of modern astrobiology. It means that a single anomalous spectrum, however suggestive, cannot carry the weight of a discovery. It needs confirmation. From a different instrument, ideally. From a different observation window. From a different analysis team using independent methods. The history of the field is full of single detection results that evaporated under scrutiny. The phosphine on Venus, the methane on Mars, which has been detected, not detected, and redetected by different teams over decades. The original arsenic-based life claim from Mono Lake in 2010, which collapsed under independent reanalysis. Every one of those was a real measurement made by competent scientists. None of them survived contact with replication. So, when the question is asked, why isn't NASA releasing the Proxima Centauri data? The most honest answer is not that they're hiding it. The most honest answer is that they're being careful, in a way the field has learned, painfully, to be careful. Releasing a spectral anomaly without context, before the team has had time to rule out the instrumental explanations, would invite exactly the kind of headline cycle that destroyed public trust in the Venus phosphine claim. The release timing is under review because the analysis is still in progress. The peer review process exists precisely so that anomalies can be tested, not amplified. That said, there are aspects of the current situation that do not fully fit the standard embargo pattern, and these are the details that have kept the story alive in the back channels. The first is the apparent scope of the analysis. Multiple groups, according to several sources, have been pulled in to look at the data. That is not normal for a routine instrument artifact. Calibration issues are usually handled by the instrument team alone. The involvement of external astrobiology specialists suggests that the team running the observation is not, at this point, confident that the anomaly is purely instrumental. They are seeking expertise in atmospheric modeling, in non-equilibrium chemistry, and the kinds of spectral features that genuine biospheres might produce. The second is the timing of the next scheduled JWST observation of the Proxima Centauri system. According to the public observation calendar, additional transits have been scheduled, and the proposal that supports those observations references the need to confirm or rule out a previous detection. The exact language is technical and intentionally vague, but the structure of the follow-up plan implies that something in the first observation window justified the use of additional, highly competitive telescope time. JWST is one of the most oversubscribed scientific instruments in human history. time on it is not granted to confirm boring results. The third, and this is the most speculative of the three, is the unusual level of coordination between JWST researchers and the SETI Institute. The SETI Institute does not typically participate in the analysis of JWST infrared spectra. Their expertise is in radio searches and technosignature theory, in the broader question of what artificial signals from another civilization might actually look like. Their involvement, if it is happening at the level being suggested, would mean that someone, somewhere, considers it worth getting their perspective on what a particular spectral feature might mean. That is not the same as saying the feature is artificial. It is closer to saying that the people responsible for the data want every possible interpretation considered before they release it. None of this proves anything. It is entirely possible, and frankly likely, that when the analysis concludes, the answer will be a subtle instrument effect. A flat field correction that wasn't applied properly. A bad pixel in the detector array. A reflection inside the optical assembly that produced a ghost feature at an unexpected wavelength. The history of astronomy is full of these resolutions, and every one of them is, in its own way, a small triumph of careful work over the temptation to believe what we wanted to be true. But it is also possible that the analysis will conclude with something stranger. The Proxima Centauri system has been at the top of every astrobiologist's target list since Proxima b was confirmed. The system was always going to be one of the first places JW still looked seriously. If there were ever going to be a moment when a near-infrared spectrograph captured something genuinely unexpected from a nearby world, it would be exactly this kind of observation, in exactly this kind of system, during exactly this phase of the mission. The architecture of the discovery, if it is a discovery, fits the pattern of how breakthroughs actually happen in science. Not announced from a podium. Confirmed quietly, slowly across multiple observation windows and multiple analysis teams until the anomaly either dissolves or hardens into a fact. What does this mean for the rest of us, watching from outside the proprietary period? It means a few specific things. It means that the question of whether we are alone in the universe has, for the first time in human history, an instrument capable of providing an answer. Not necessarily a final answer, and certainly not the kind of answer that arrives with a fleet of spacecraft over Manhattan. The kind of answer that arrives as a chemical fingerprint in a spectrum, indicating that the atmosphere of a planet 4.24 light-years away is doing something that no purely geological process can explain. Oxygen in disequilibrium with methane. Industrial pollutants. Refrigerant gases that are stable only when manufactured. JWST is not built to detect intelligent signals in the SETI sense. It is built to detect the chemical waste, intentional or not, of any biosphere or technosphere within its reach. And Proxima b is, by a wide margin, within its reach. It means that the public conversation around astrobiology is about to enter a new phase, regardless of what the specific Proxima Centauri data turns out to mean. The fact that researchers are now treating an anomaly from another star system with the kind of seriousness usually reserved for major theoretical discoveries says something about where the field is and where it expects to be in the next decade. We are not, as a species, going to be debating whether life beyond Earth is possible for much longer. We are going to be debating what specific atmospheric signatures count as evidence and how confident we can be in the data behind them. That is a profoundly different conversation than the one we were having 10 years ago. And it means that the question of how scientific institutions communicate uncertainty is about to be tested at a scale and intensity those institutions have never faced before. NASA's caution around the current data is, from the inside, prudent. From the outside, it is being read by many people as evasion. The gap between those two readings is going to widen as the analysis continues. The institutions involved are going to have to find ways of saying clearly and publicly that careful work takes time, that the alternative to careful work is the slow-motion embarrassment of the BLC-1 cycle repeated on an even larger stage, and that the absence of an immediate announcement is not the same as the absence of a result. That communication challenge may, in the long run, matter as much as the science itself. The next scheduled observation window opens in approximately 3 months. If the anomaly is instrumental, the follow-up data will almost certainly reveal it. If the anomaly is real, the follow-up data will either confirm it or fail to confirm it, or, in the messy way these things usually unfold, produce a result that's harder to interpret than the first one. There is no version of the next year in which we do not learn something significant from this observation. Either the anomaly resolves into a calibration footnote, and the field learns something useful about the long-term behavior of NIR spec at the edges of its design specifications, or it resolves into something else. Here is what we know, restated cleanly for the record. The James Webb Space Telescope, operating from L2 with its 6.5-meter mirror and its near-infrared spectrograph, observed the Proxima Centauri system during a scheduled window earlier this year. The observation produced spectral features that the analysis team has so far declined to fully characterize publicly. The data is currently in the standard proprietary period, with internal peer review still in progress. The previous high-profile signal from the same star system, BLC-1, was retracted in 2021 as terrestrial interference. The scientific community's most prominent skeptics are emphasizing the likelihood of instrumental artifacts, particularly calibration drift and order overlap, as the leading non-exotic explanations. The next observation window for the same target is scheduled, and the proposal supporting it references the need to confirm or rule out a previous detection. What we do not know, and what cannot honestly be claimed, in the absence of the full analysis, is what the feature represents. We do not know whether it is real. We do not know whether, if real, it has a biological, geological, or otherwise natural explanation. We do not know whether the SETI Institute's involvement, if it is occurring, reflects a serious consideration of technosignatures or a routine cross-check. We do not know when the data will be released, only that the timing is under review. The WOW signal in 1977 was a 72-second burst at the 21-centimeter hydrogen line, recorded by a volunteer astronomer at Ohio State, scribbled with the word WOW in the margin of the printout. It has never been explained, never been repeated, never been ruled in or ruled out. It sits in the historical record as the closest thing the SETI program has to a candidate, and it sits there precisely because no follow-up observation ever caught it again. The Proxima Centauri NIR spec feature, whatever it turns out to be, is not going to share the fate of the WOW signal. JWST can return to the same target. The follow-up is scheduled. The analysis is ongoing. In a field that has spent 50 years waiting for a signal that could be confirmed, we are about to find out what happens when confirmation actually becomes possible. The result will be either the most consequential observation in the history of astronomy, or the most carefully resolved false alarm in the history of the field. Either outcome will change how we do this work. The clock is running. The next observation window opens in spring, and somewhere inside the data already collected, in a series of numbers stored on servers in Baltimore, sits an answer that nobody, yet, is in a position to give.